Hello, everyone, and welcome back to our conversation about chemical equilibrium, where we're now going to get into the nitty-gritty of how to calculate chemical quantities for a reaction that exists at equilibrium. So let's go ahead and get started with an example. So I have given us this chemical reaction here, where we have two COF2 gas molecules that decompose in a decomposition equilibrium to create CF4 and CO2 gas. We are told that we are at equilibrium, and we're also given the equilibrium constant Kc. So let's make a note that that is our equilibrium constant that is expressed in terms of concentration or molarity. And we were given, if at equilibrium, partial pressures. Okay, if we see this word partial pressure, this kind of brings Kp to mind. So we might need something that allows us to convert between Kc and Kp. But I've been given the partial pressures of each of my products. Nope, I got one reactant here. So I know that the partial pressure of this at equilibrium is equal to 0.255 atmospheres. And we know the partial pressure of CF4. Partial pressure of CF4 is 0.118 atmospheres. And we are asked to find, so always a good idea to identify our goal. What is the partial pressure of CO2? So our goal is to identify the partial pressure at equilibrium of CO2 if we are at a reaction condition of 1,000 degrees C. So let's start by maybe writing out what we know about Kp, since we're given things expressed in terms of pressures. So we know that Kp is our equilibrium constant expressed not in terms of concentration, but with respect to partial pressures. So this is going to be my pressure of my products at equilibrium. So pressure of this at equilibrium and pressure of this at equilibrium. Both of those are in the stoichiometric proportion of 1, meaning their coefficients are 1. So I've got the pressure of CF4 times the pressure of CO2, with the understanding that these have to be our equilibrium partial pressures if they are going to be included or expressed in our equilibrium constant K. And we knew that because we were told that we existed at equilibrium with these pressures. So we're good there. And then our product partial pressures have to be divided by our reactant partial pressure. So this is our partial pressure of COF2. And notice that COF2 has the stoichiometric coefficient of 2, so this partial pressure needs to be squared. So our goal is to solve for this, the partial pressure of CO2. All right. Let's maybe rearrange this so that the partial pressure of CO2 is isolated, because that's what we're trying to find. So this would be Kp times, moving over my denominator, partial pressure of CO2 squared over partial pressure of CF4. And I do, in fact, know these partial pressures at equilibrium. So this is 0.4 CO2, no, not CO2. What am I doing here? CF4, COF2, there we go. So partial pressure of COF2, 0.255 atmospheres squared over our partial pressure of CF4, which was 0.188 atmospheres, meaning that our partial pressure of CO2 at equilibrium is equal to Kp times this value. So let's get what this value is. So 0.255 squared divided by 0.188. This gives me 0.345877. And this would be atmospheres, because I've got atmospheres squared over atmospheres. So I am really close to finding this partial pressure. However, I was not given the equilibrium constant in terms of pressure. I was given Kc, so I need to convert to Kc. And the way that I'm going to do that is by using the relationship that says Kc is equal to a bunch of stuff done to our, see, our gas phase derivation. So this is equal to R1 over RT raised to the exponent rules times Kp. In other words, Kp is equal to Kc over 1 over RT raised to the exponent rules. So what are these exponent rules here for us? So in our original Kp, we had 2 over 1. So this meant that our expression was going to have ultimately a net like base raised to the 2 minus 1, which equals 1, which makes our life nice and simple because the exponent rules there make this so that what we have to multiply this constant by is simply equal to 1. So in our case, since we had p squared over p, the exponent equals to 1. So that means that Kp is equal to Kc divided by 1 over RT, or times RT. So that's going to be our Kc of 2.00 times our R, 0.08206 liter atmospheres per mole Kelvin, times our temperature, which needs to be in Kelvin. We were given our temperature of 1,000 degrees, add 273.15. So this is times 1,273.15 Kelvin. Down here, we're running out of room a little bit. And so we need to figure out what Kp is. So that's 2 times our gas constant, 0.08206. And then times our temperature in Kelvin, 1273.15. I get a Kp equal to 208.9 sub 5. And now that we have Kp, we can take this Kp and plug it in here to solve for PCO2. So we had again that our partial pressure of CO2 at equilibrium is equal to Kp times our partial pressure of, I believe it was COF2 over our partial pressure of CF4 at equilibrium. We have already done ourselves a favor of figuring out what that quotient was. And now we need to substitute in our KP. So KP, we know this was our 208.95. And then our resulting pressure quotient was 0.345 sub 887. Atmospheres. So when we do this little product, I get a partial pressure of CO2 at equilibrium equal to 72.27 or 72.3 atmospheres. Okay. Now this seems kind of high to me. Should probably go back and check that we've got our conversion and exponent rules down so that we did this conversion correctly, right? Because we were given Kc and we needed Kp in order to solve for a partial pressure. So check this work on your own. And in our next video series, we're going to ask ourselves the question of, okay, like, yeah, in a question like this one, we were given information about the system at equilibrium. So like we were able to do some stoichiometry, some calculations, some quantifications of what's going on when we already know the equilibrium quantities, here pressures, of all of our substances involved in the reaction. So on our next slide, we're going to talk about what if we don't know how like our quantities exist at equilibrium, right? Like what if we only know things about the initial states? How can we solve for what's going on at equilibrium? So in this example, our situation at equilibrium was known, and we're now moving into the stoichiometry where we have to calculate quantities of a system that is in equilibrium, but we don't know anything about those equilibrium quantities. So how do we get them? So that's what's coming up. See you in our next video.